Hi everyone, my name is Zhang, and I'm a deep learning software engineer at NVIDIA. Today, I'm presenting horizontally fused training array, an effective hardware utilization squeezer for training novel deep learning models. This is a leftover work from our grad school back at the University of Toronto. This is also a collaboration between me, Ming, Yuxuan, Xin, and my advisor Gennady. We open source our work at the top left GitHub link. Let me kick off the talk with a summary. Driven by the tremendous efforts in deep learning research, the training cost for developing new models increases dramatically. From real research workloads, we found that repetitive single accelerator training jobs, such as for hyperparameter tuning, can dominate the cluster-wide resource consumption and have extremely low hardware utilization. To address this problem, we propose horizontally fused training array, or in short HFTA, which horizontally fuses the model among jobs deeply down to operators and train those models simultaneously on a shared accelerator. Compared to the standard practice of training each model on a separate accelerator, our method can achieve up to 11.5x on the A100 GPUs and up to 15.1x on TPU v3. Let me first introduce some background and motivations. As we know, deep learning research often involves training a diverse set of models. And the number of DL researchers is also growing fast, as we can see from the number of papers being submitted to top ML conferences such as NeurIPS. As a result, the demand of compute resource for training also increases rapidly. Now, if you are the one who provides resource to training, such as an AI research institution, for many good reasons such as saving costs or even environmental concerns, you want to make sure that the resources you provide are put to good use. In case of you don't know, the Vector Institute is one of such AI research institutions. To get better insights into the hardware efficiency achieved by typical training jobs, we collect and studied the cluster-wide GPU usage statistics for 2 months, including 51K jobs and 472K GPU hours. To our surprise, we found that single GPU training jobs dominate the cluster-wide GPU hour usage. Additionally, most of those jobs are repetitive, which refers to many concurrent job instances with the same program but configured differently. They are usually for hyperparameter tuning or convergence stability testing purposes. If we take a closer look into their utilization metric, we see that they often have low hardware utilization. Now, why does this happen? The reasons are twofold, from both the DL side and the hardware side. Let me explain each fold. On one hand, performance optimization is hard, and this is even more true for DL researchers and practitioners who are often computer system and architecture novices. Now you might ask, what about just increasing the batch size? Unfortunately, increasing the batch size does not work universally, as prior work already studied, due to problems such as generalization gap and batch size scaling limits. On the other hand, DL accelerators are getting more and more powerful, and we can clearly see this trend from the recent releases of both NVIDIA data center GPUs and Google Cloud TPUs. Thus, if we have a workload that is already optimized, it will be even harder to make it well utilize a better hardware. Now that we know what the problem is, how can we possibly improve hardware utilization? Well, I have an idea. We can train multiple models on the same accelerator at the same time. Currently, we can do this on some accelerators that have special features to support sharing among arbitrary processes, such as the MPS and MIG on NVIDIA GPUs. However, as we later show in our evaluation results, both features are less effective for repetitive training jobs. Additionally, other accelerators such as TPUs currently do not have such features whatsoever. So, how can we possibly enable efficient sharing for repetitive training jobs on any types of accelerators? In our work, we can achieve this by leveraging the following unique characteristics. And let me explain this with an example. Say that you are tuning the learning rates for a model. The exact choice of the learning rates is not going to change the types of operators for the model, since you still need the same linear, ReLU, and so on. And the shapes of those operators, which ultimately depends on the shape of all the input tensors, are going to stay the same as well. This means that when launched repetitively, such as doing hyperparameter tuning, the models among jobs often have the same types of operators with the same shapes. Now you might ask, what can we do with this observation? Well, we propose intermodal horizontal operator fusion to fuse similar models together so that we can test all hyperparameters on the same accelerator at the same time. Unfortunately, existing DL stack, including both high-level frameworks and low-level device-specific operator library, are all designed for training each model on a separate accelerator. So, how can we possibly train fused model without reinventing everything from scratch? To answer this question, we make our second observation that horizontally fused operators can often lead to other existing mathematically equivalent operators. And let me use another example to illustrate this point. The fully connected layers are often implemented by matrix multiplications, and fusing multiple matrix multiplication together can be realized using an operator called batch matrix multiplication, or in short, BMM. Normally, BMM is used in the multi-head attention layers often found in transformer-based models. Therefore, many DL frameworks already have fairly well-optimized BMM implementations. Now you might ask, this is just fully connected layers, what about other operators? Indeed, different operators often require different ways to reuse existing implementations, and DL researchers and practitioners would definitely need a tool to facilitate our proposed intermodal horizontal fusion. Therefore, we developed a DL framework extension library called Horizontally Fused Training Array, or in short, HFTA, specifically for this purpose. We built HFTA on top of PyTorch due to its training popularity among the ML community, which is HFTA's targeted user group. However, the same idea can be applied on top of other frameworks as well. Since we do not introduce any new device-specific operator implementations, HFTA can support all the hardware backend that the framework already supports. In the case of PyTorch, HFTA can support all NVIDIA GPUs and Google Cloud TPUs. Let's take a closer look into the components that HFTA offers. HFTA currently supports 18 different operators that are common in DL research. I will refer to a paper for the exact fusion rules of each of those operators, but just to give another example, horizontally fusing multiple convolutions together can be realized using the group convolution by concatenating the inputs and filters along the channel dimensions. Is there anything else that we can fuse? Well, HFTA can also support fused optimizers and learning rate schedulers. Even though the exact update rules are different for different optimizers, on a high level, fusions can be implemented by replacing the original scalar vector dot products with broadcasted vector vector dot products. Are these all that we can fuse? As it turned out, we can fuse the loss functions as well. If the loss is reduced by averaging over the media batch, we need to scale the fuse loss value by the number of models that contribute to this loss. I will refer to a paper for the detailed derivations on why this is needed. I want to highlight that all the aforementioned transformations are mathematically equivalent. Thus, we preserve the original convergence behavior of the model. To validate this empirically, we train ResNet 18 on Cepher 10 with 3 different learning rates, either as 3 separate training jobs, or as a fused training job via HFTA. We can see that their training curves overlap completely, which means that HFTA has no impact on the convergence. Now, what about the training throughputs? Just like any other research projects, we want to evaluate our idea and make sure that the results are reproducible. We perform experiments on 3 state-of-the-art NVIDIA data center GPUs across 3 architecture generations. The V100 from AWS, RTX 6000 from a Vector Institute's local cluster nodes, and the A100 from GCP. We also evaluate on TPU V3, which is also from GCP. We perform experiments across different versions of the DL stack. Our first baseline is called serial, in which case we train each model on a separate accelerator. This is the common practice employed by most hyperparameter tuning frameworks. Some accelerators, such as NVIDIA GPUs, also support running multiple processes at the same time, in which case we have a few stronger baselines. Our second stronger baseline is called concurrence, in which case kernels from different models are time multiplexed. We also have a stronger baseline on the MPS feature. When a single kernel does not fully use all GPU resources, MPS would co-run kernels from different processes on the leftover resources. Our last stronger baseline is on the MIG feature, which slices the GPU into no more than 7 partitions, and we train each model on a separate partition. This feature is only available on the A100 GPU. We evaluate across a wide range of models and tasks. Because we want to know how useful HFT can be to DL researchers and practitioners who often lack advanced optimization experience, let's first look at the results on the PointNet model with the point cloud classification task, which is yet intensively optimized by computer system and architecture experts. As for our main results, I'm showing the FP32 training throughputs as we keep sharing the same V100 with more models until equal to auto memory error. This includes serial, concurrence, MPS, and HFTA. From this figure, we can make the following observations. First, HFT can achieve significantly higher peak training throughputs than serial, concurrence, and MPS. Second, if we fix the memory budgets, HFT can co-train more models than both MPS and concurrence. Third, even with the same number of models on the same GPU, HFT can often achieve higher training throughputs than all baselines. Now, what about mixed precision training? Well, in this figure, in addition to the FP32 training results, I'm also showing the EMP results in the solid curves. From this figure, we can see that HFT can better exploit advanced hardware compute units such as the tensor cores during EMP training than all baselines. What about different GPUs? Let's take a look at the HFT's hardware sensitivity by comparing the results between RTX 6000 and the A100s. On A100s, we additionally have the MIG baseline since the MIG feature is only available to the A100 GPU. We can see that since A100 has a higher memory capacity than RTX 6000, HFT can fit more models on A100s. Coupled with the fact that A100 also has a higher flops than RTX 6000, HFT can achieve higher speedup on A100s. Intuitively, this means that if the workload is already unoptimized, simply switching to better hardware will lead to more underutilization. As an analogy, if you are a bad cook, simply switching to professional cooking equipment is not going to give better taste to your food. Lastly, MIG's partitioning scheme can be too coarse-grained, since even MPS allows sharing the GPU with more than 7 models. Now, what about a completely different accelerator? On TPU-v3, which currently does not have any hardware sharing features, HFT can achieve significantly higher training throughputs than serial as well. Now that we know HFTA is very effective, you probably wonder why it is. To answer this question, let's first measure the GPU memory footprints between MPS and HFTA. We found that when we train a single model, the footprints between MPS and HFT are the same. However, when we train 2 models on the same GPU, HFTA suddenly takes less memory. Now, why is that? This is because the DL framework stack reserves a certain amount of memory, which is essentially overhead associated to the training process. Therefore, training each model in separate process as MPS does essentially duplicates this overhead. Are there any other reasons why HFT is more effective? Aside from the savings on GPU memory footprints, HFT can also improve the utilization of the compute units. The following 3 figures list the hardware performance counters on A100s, including SM active, SM occupancy, and tensor active. If you have a background in GPU architecture, I'm listing the exact definitions of those metrics here. If you don't know anything about GPU architecture, just know that those metrics are all proxy on different aspects of GPU utilization. We can see that even though MPS and MIG can be somewhat effective, HFT is a lot more effective, and this is true across all 3 metrics. Our paper has a lot more results than what I can cover in this talk. including the experiments on the rest of our benchmarks, which are a lot. In fact, we spent more than $15K running all of those experiments, and most of the money went to measuring all the baselines since they are so inefficient. In summary, HFT can achieve significantly higher training throughputs than all baselines on both TPUs and GPUs. Additionally, we have an initial investigation into how HFT can be integrated with hyperparameter tuning algorithms. And we found that HFT can reduce the total GPU hour for tuning by up to 5.1x. Furthermore, we have a performance sensitivity study on what happens if the models cannot be fully fused. With that, I'm going to conclude this talk. From real research workloads, we found that repetitive single accelerator training jobs, such as for hyperparameter tuning, can dominate the cluster-wide resource consumption and have extremely low hardware utilization. To address this problem, we propose horizontally fused training array, or in short HFTA, which horizontally fuses the models among jobs deeply down to operators, and we train those models simultaneously on a shared accelerator. We hope that our work can inspire future research on making hardware usage optimizations easier for the ML community. Last but not least, we open source HFTA, and we welcome everyone to try it out. Thanks a lot for attending my talk.